In section 10.3, we're now ready to look at the next type of conic section. We've covered circles, we've covered ellipses. The third type we're going to look at in detail is the hyperbola. In the next section following this, we'll finish up with the parabola, but now let's talk about the hyperbola. As we did with the ellipse, we're going to start with the formal definition of the particular conic section we're looking at now. We're looking at hyperbolas. So, formally, given 2 points, again calling them foci, or focus in plural, we will define the set of all points such that the difference of the distances to the foci is constant. Now, do you remember in ellipses we said that the sum of the distances was constant? Now we're going to take the difference, we're going to subtract them, and we're going to hold that constant. That shape is called a hyperbola. Now that's the formal definition, and I think it's really, for me, hard to visualize what that says. Let me draw you a quick picture, and I don't think it'll help a whole lot, but it's still something to consider. What I think the best and easiest way to picture a hyperbola is that shape that we saw in previous section, where we saw a plane intersecting the cone. That shape is the hyperbola. But formally, mathematically speaking, in terms of distances and that sort of thing, if you have 2 points called the foci on, say, either side of some line here, and you look at a point that I'm going to say is on the hyperbola, if I measure the distance to one foci and the distance to the other foci, and I took another point that's also on the hyperbola, and I measured the distance to each of the foci there. So this was D1, D2, D3, D4. What I'm saying is for any 2 points, the difference is constant. Okay, and the shape, we've seen it, looks something like this. Kind of hard to see my wonderful picture here, but that's the hyperbola. We'll get a better idea of what's going on here when I do some examples. Okay, now what's the equation for the hyperbola? That's really the most important thing. And the only type of hyperbola we're going to look at in this course is the hyperbola that is centered at the origin. It looks just like the equation for the ellipse. X squared over a squared, y squared over b squared equals 1, but instead of a plus, there's a minus. When there's a minus, it's a hyperbola. Now you can also have it going the other direction, y squared over b squared minus x squared over a squared. You can subtract y minus x. Still equal to 1. You'll get 2 different hyperbolas. In fact, this hyperbola, when you take x subtracting y, x squared over a squared minus y squared over b squared, is a left-right hyperbola. Right? It means it has 2 pieces, one going to the opening to the left, one opening to the right. In this case, the shape of this graph is an up-down hyperbola, one going up and one opening downward. Okay? But here's how we graph that. Let's go through the steps, because it's a step-by-step procedure that you've got to learn to get the graph of the hyperbola just right. The first step is to find the a and the b. So the number is underneath the x and the y. The a squared is always under the x squared, so the a in this case is the square root of 49, which is 7, and the b is the square root of the 16, which is 4. So first thing you do before anything else is find the a and the b. Then what you're going to do is you're going to draw a dotted line box about the origin, where the dimensions are a in the x direction left and right, b in the y direction up and down. So in this case, I'm going to go 7 to the right. 1, 2, 3, 4, 5, 6, 7. 7 to the left. 1, 2, 3, 4, 5, 6, 7. I'm going to go up. 1, 2, 3, 4, 5. It's 4 up. Actually, I only needed 4. And down 4. 1, 2, 3, 4. And I'm going to draw a box. Dotted line, because the dotted line is only a guide to the graph. It's not actually part of the graph. I'm going to draw a box with those dimensions. That is, it goes up 4, over 7, over 7, down 4, down 4, and then back across. I drew a dotted line box, okay, that went up 4, down 4, right 7, left 7. Okay, and I'm going to take this picture and move it to the next page for us. So we put our graph down here. The next step, the third step, is to draw dotted line asymptotes through the corners. Okay, what that means is I'm going to draw some lines. I'm going to call them asymptotes. Asymptotes are in mathematics things that are lines that the curve gets close to but never crosses. So all I'm doing is drawing straight lines that go through the diagonals, or that are the diagonals. Now the equations for these asymptotes are always going to be the same. It's always y is equal to b over a x, and y is equal to negative b over a x. There's two different lines. There's the positive slope and the negative slope. Okay, and that's what the equations for the asymptotes are. Now you draw the hyperbola. If x is first, meaning if it's an x squared minus a y squared, then it is a left-right hyperbola. Now in our example, that's what we have. Scan back to the previous page. We had x squared over 49 minus y squared over 16 equals 1, which means it's going to be left and right. So it opens in the left and the right piece. If y had been first, it would have been an up-down, and we would have graphed it up in the top and the bottom piece. But as it is, we're going to put a point right there on the edge of that box, a point right there on the edge of that box. We're going to draw a curve from that point that gets closer and closer to that line, but doesn't cross it. A line that gets closer and closer, but doesn't cross it. That solid line I just drew on both pieces is the equation, is the graph of the original equation that we had. X squared over 49 minus y squared over 16 is equal to 1. That hyperbola is the graph, the set of all points that satisfy that equation. That's what you do every time. Okay, what you do is you make sure it's in standard form, you find out the a, the b, you draw the box, you draw the asymptotes, then you draw the hyperbola. Let's do one more example just for practice sake. In this problem, we have 4y squared minus 25x squared is equal to 100. The first step is we need to get this equal to 1. So I'm going to take everything and divide it like we did for ellipses as well. We're going to divide everything by 100. 4 goes into 100 and 4 both. You divide 4 out of 4, you get 1. You divide 4 out of 100, you get 25. So I end up with y squared over 25 when I reduce the first fraction. Minus 25 goes into 25 once, and 25 goes into 100 4 times. So it's x squared over 4 is equal to 1. 100 divided by 100 is 1. So our a would be the square root of 4. Remember, a is always under the x, and it's the square root of that number. So a is 2. b is the square root of 25, which would be 5. So my box, my guide box, is going to go left and right 2 and up and down 5. So draw the box with those dimensions and then draw the diagonals. Now, is this an up-down parabola or a left-right parabola? Well, because the y is first, it's going to be up and down, which means I put a point here and a point here, and I draw a curve that goes from that point out towards that line, get closer and closer, and doesn't touch it, and it goes on forever in each direction. Voila. Okay, the solid line is your hyperbola. All right, and that's it. That's the end of section 10.3.